Great. Hi, everybody. I'm Jasmine, and as you just heard, I'll be telling you about inferring task context for continual learning. Oh no. I will try to tell you about inferring task context for continual learning. Okay, so say we want to train a neural network to do image classification. Specifically, we want it to be able to classify dogs versus cats. How would we go about collecting a data set for this? Well, first, we would get images of dogs. We'd label them as dog. We'd get images of cats. We'd label them as cat. And then we'd shuffle all of our collected data and sample sets of images to show to our network. As a result, this is what our model would see: a set of images from the classes that we care about with no general structure or relationship between the pairs of images. We refer to this generally as a data set. This is in stark contrast to the data that humans learn from. We understand the visual world through video. The image samples that we see are generally ordered, they're organized by time, and there is a relationship between nearby images in the video. I'll refer to this as a data stream. So why don't we, for example, train our neural networks closer to the way that humans learn? With our dog-cat classifier, why don't we train it first on videos of dogs, and then train it on videos of cats? In this setting, we'd want to learn both animal classes, but in an incremental way. Consider the following data stream. If we're trying to learn from a data stream, we can think of the stream as consisting of multiple discrete tasks. Like in Nando's talk, I'll use the word task a bit loosely. So in this example, we can think of having two different tasks, and task 1 would correspond to learning to classify dogs, and task 2 would be learning to classify cats. So we could think of this data stream as having some underlying structure, and that the first 3 frames come from the same task, the next 3 frames are from a different task, and then we switch back to the original task. The problem is that our neural network has no idea about the task structure of this data stream. Instead, it only sees images at the individual sample level. So if we train our model on this stream of images, it's likely that our network will overfit to the current time point. And to understand what this means, let's go through a possible training trajectory and what it could look like. If we initialize our model from scratch and show it this first image, it might get lucky and happen to predict dog. In this case, it's correct. We show it the next image, it's seen dogs before, so it predicts dog. Third image, dog. And now we have this next image, which is actually a picture of a cat. But because the network has only ever known dogs, it calls this a dog and is incorrect. Based on feedback from the previous iteration, maybe it switches its prediction to cat, cat again. And now when we show the model this final image, it's so used to classifying cats that it incorrectly calls this dog a cat. We refer to this phenomenon of overfitting in time as the problem of catastrophic forgetting. Our model has forgotten about a previously learned task in favor of a more recent task. And in order to talk about forgetting, we also need to talk about memory. So we can think of the weights or parameters of our model as a form of memory. And in the standard learning paradigm, where our network learns from a data set of unorganized samples, we can use the same memory to learn about multiple tasks, and we don't see forgetting because each task is typically well represented at each time point. But in the setting of learning on a continually changing data stream, we find that our memory of old tasks gets overwritten by new tasks. A solution to this problem might be to keep memories separate for each individual task, but in order to do this, we need to know about the underlying structure of the data stream. So I've alluded to the 2 ingredients that we're going to use to alleviate forgetting while training a neural network on a data stream. And they are, first, given the data stream, the network has to determine what task it's in, and then given that information, it needs to store or retrieve a relevant memory for that task. So first I'll talk about determining task structure from a data stream. And before diving in, I want to take a short detour to some prior work. Hidden Markov models and Kalman filters are classic approaches to modeling sequential data, for example, a data stream. And there's been some prior work using switching Kalman filters to infer context changes on naturalistic video. But this work isn't necessarily tied to the problem of continual learning. Within continual learning, there's been several deep learning-based approaches to prevent forgetting on a data stream. And this is by far not an exhaustive list. But these methods often assume that the task structure of the data stream is already given, and now the goal is to prevent interference between the learned tasks. Much less work has been done on the problem of inferring task structure without supervision. Existing approaches either employ an auxiliary module to infer task structure, or they build a generative model of the data, or both. And depending on how complicated the method is, they don't necessarily scale well to larger data streams. In this work, I'll describe a simpler approach to inferring task structure that is simple and integrated with the primary model that we care about training. And before I specify the approach, I want to give some intuition for how it works. So let's go back to our example of a dog-cat classifier and say this model has already been trained on several images of dogs and cats, and it's able to classify new examples with high accuracy. So we'll start by feeding this model a new image, and one thing that we can do is look at the population response of the neurons in the first layer given this image. This response is well characterized by the distribution of activations, and maybe because this image is similar to previously seen cat images, our activations will look like they are in some expected distribution. And we can do the same thing for the second layer, and also observe that they are distributed as expected. Finally, our network makes a prediction. Here we have another cat image, and we pass it through our network and look at the activations at each layer, and we observe that our activation distribution is as we expect again. We can interpret this image as being familiar to the network. Now the network encounters an unfamiliar image from a distribution outside of the one that it was trained on, and if we look at the distribution of activations in the first layer, we find that it's no longer what we expect, and the same is true for the next layer. So how do we turn this intuition into a tool that can be used to detect task change? Well, first we need to know, for images that the network is familiar with, what typical activations look like. And since we don't necessarily know this, we can instead impose a prior distribution that we want our activations to look like they're drawn from. For example, we can impose that we want our activations to look like they're drawn from a standard normal distribution. And this can be achieved by adding a training loss, which I'll refer to as a familiarity loss, that measures the divergence between the current activation distribution and a standard normal distribution, and we can minimize this loss over a data set or over a data stream. And if we add this loss to our training objective, over the course of training, our network will learn to be good at both classifying dogs and cats while having activations that are normally distributed. When an out-of-distribution or unfamiliar visual input is presented because the task has changed, we might no longer expect that the network activations look like the prior distribution. And as a result, the scale divergence measured by our familiarity loss will be high, and this can serve as an indicator that this data is part of a new task. I'll also note that this familiarity loss is not necessarily at odds with the training task, depending on how much this loss is weighted relative to the primary supervised learning objective. Sometimes, actually, it's able to accelerate training, and there's more information about that in this archive paper. So now that I've talked about a method for determining task changes in a data stream, I'll talk about how we can use that task information to store or retrieve relevant memories in order to alleviate forgetting. This is the standard linear equation that's shared across many learning models, and it makes up the forward pass of a neural network. For simplicity, we'll call this the first layer of the network, so that means that X represents the input data. And in the standard setting, we don't necessarily assume a relationship between X's in different time points. In continual learning on a data stream, there's this extra unobserved variable k, which, recall, corresponds to the specific task that a data point in a data stream belongs to. But now we can see that the weight matrix, or the memory, is not accounting for this task at all. And as a result, we might see catastrophic forgetting. So we can augment our standard equation to include a task-dependent context, C. And the goal is to infer this from the data. This augmented equation has two interpretations. In the first, we have a single memory W and a context matrix, which I'm denoting by C, and this can be used to transform the data X in a way that will make it familiar to the memory. This interpretation makes sense if our data stream contains tasks that are basically the same, aside from a simple visual transformation. We want to learn to transform the data into a space where all of the tasks are identical. Many transformations in the natural world are geometric, and so in this case, we can restrict the context matrix C to represent an affine transformation over the coordinate space of the input. The index K into C represents the parameters of that transformation, and those are what we want to infer from the data stream. In the second interpretation, we can see context is acting upon the memory instead of on the data. And first, we assume that our overall memory, W, actually represents multiple memories stored together in superposition. In this interpretation, context acts as a tool which allows us to store and retrieve multiple memories within a larger weight matrix without interference. In this setting, the context Cs are fixed random diagonal matrices, and rather than being learned, the goal is to infer the task index, 1 of k, from a data stream. Once we have this index, we can use the corresponding context matrix to unlock the correct memory in W. And this interpretation often makes sense when the data stream is composed of tasks that have little shared information. And in this case, we want to keep the acquired knowledge separate for each task. So just in case you catastrophically forgot about the methods that we just talked about, here is one last reminder before I move on to some experiments. We're going to use a familiarity loss to detect task change, and given that task information, we'll alleviate forgetting by using model superposition. This first experiment highlights the superposition interpretation that we only have a single memory, and context is used to make unfamiliar inputs familiar to the memory. So we set up an experiment where we trained on the standard MNIT digit classification task, and then at test time, we present the trained network with digits in an orientation that's never seen before. Before the network classifies the image, we optimize the parameters of the context matrix to minimize our measure of how familiar the data is to the memory. And remember, in this setting, our context corresponds to a geometric transformation of the data. So on the left, we can see these unfamiliar digits, these digits in an unfamiliar orientation, and on the right, we're going to see the resulting transformation that's generated by optimizing the context parameters so that the data is familiar to the learned memory. And as we just saw, in order to minimize this familiarity loss, the network transforms the data to its canonical view, defined as the view that it saw during training. So next, let's consider an example of the other model superposition interpretation, where context is used to access separate memories. This is an example of a data stream called permuting MNIST, and in this stream, task 1 corresponds to the standard MNIST dataset, and task 2 is generated by applying a fixed random permutation to all the data points in task 1. While other methods for continual learning use this data stream, they assume that the task structure of the data stream is already known. And we want to consider the case where we simply observe the data stream and we have to infer the task structure. If we plot our familiarity measure as a function of training steps, we see the following behavior. As the underlying task changes and the data stream becomes visually different, the loss spikes. And because the task boundaries are so clearly given by these spikes in the loss, we can set a simple threshold, and when the loss exceeds this value, assume that the data stream has changed and retrieve a different memory from our weights in superposition. And one way to measure forgetting is to look at the accuracy of the first task as a function of additional training tasks. So in red, we can see a model that uses a single context for the entire data stream, and as expected, this model experiences forgetting. And in blue is our described approach for inferring task context from data alone in order to learn separate memories in superposition. This model largely retains accuracy on the first task even after 9 additional training tasks are added. So I've showed some ways to infer task structure and prevent forgetting on examples of simple data streams, but remember the original motivation, which was that we want to enable neural networks to learn from the same data that humans learn from. The rotated and permuted MNIST datasets we've considered up until now are problems that are studied by the community, but they're a bit toy because they're not really data streams. They're data sets for supervised learning that have been turned into data streams so that they can be used for continual learning. And this is ignoring the fact that we have a natural and abundant source of continual learning data streams, which is video from the actual world. This data source is especially interesting for inferring task structure because there's no ground truth labels like task 1 and task 2, and the idea of context depends on the application. One obvious thing stopping us from using arbitrary real-world videos is that we need annotations for some downstream task, like classification or segmentation. But instead of focusing on a task that might need labels that are hard to get, there are many ways to generate labels for free and essentially self-supervise the learning process. For example, we could auto-encode the data, we can predict the next frame of a video, or we can predict color channels from grayscale. And in this case, we focus on the task of image colorization. So I'm about to show you a video of our method applied to a realistic data stream, which happens to be a birdwatching video that is part of a YouTube phenomenon called Cat TV. And in the upper left, we plot the input video, and on the upper right is the colorized output from our model. On the lower left, I'm plotting the familiarity loss, which is the measure of how familiar our network is with a given frame. And in red is a threshold that if the loss exceeds, the model will switch context. The context is shown in the right, the context that the model is using, and in this case, we only have 2 contexts. So to colorize the input, we find that the model learns to switch context based on the arrival and departure of the birds. And in this example, task 1 corresponds to frames without the birds, and task 2 corresponds to frames with birds. So in summary, I've talked about different ways to use and interpret context for continual learning. I've discussed how we can use context to transform novel images in a way that make them more familiar to a memory. I've shown how specific memories and superposition can be stored and retrieved to alleviate catastrophic forgetting. And finally, I've shown a first step towards inferring task structure on natural video by using only self-supervision. So in this work, we either enforce that the context is a spatial transformation, or we used context as a tool to keep memories entirely separate. But in the real world, there's a variety of different types of natural transformations that exist in data streams, and we can't hope to be able to specify all of them. Rather than fixing the structure of the context, we ultimately want to learn the structure of the context from the data stream itself. Doing so would allow models to learn about visual transformations without explicit supervision and get us a step closer to enabling neural networks to truly learn continually in the natural world. So I want to say thanks to my collaborators and also to you for your attention, and I'll take any questions now.
So thanks for this great take on continual learning and identifying task structure. I really enjoyed. So what would be your idea about identifying task structure if the image statistics stays basically the same, but the task requirement changes? So if you really cannot infer anything from the visual input alone, but have to look on the task demands.
Yeah, that's an interesting question. I mean, I think in that case, there's nothing you can do except for take in like an additional input that specifies the task that you want to do. So like you can see an image, but somebody needs to tell you whether or not you want to classify that image or segment that image. And you can imagine taking some auxiliary information if the task context does not in fact depend on the visual input.
All right. In the interest of our decaffeinated souls, I think we want to give some time for the coffee break. So thank the speaker and thank the whole session. Very nice.